Here is our final project, which is entitled as AES-128 Hardware Software Co-Design on SoC FPGA, which is supervised by Dr. Benjamin Karen Safar sir, and submitted by Sam and Aryan. And here we go to the project overview. Here we introduced our introduction, system architecture, perform HPS plain text input and key generating, and also perform HPS FPGA memory mapped AXI, and also demonstrate a fully working hardware software integrated system. Here we go to the introduction. Basically, FPGA is widely used to accelerate computationally intensive applications such as cryptography. And this project presents a complete hardware software co-design implementation of AES-128 encryption and decryption using SoC FPGA. And then the board we are using is D1 SoC board. And here we go to the system architecture. There are mainly three components: the HPS, FPGA fabric, and AXI interface. So here we go to like HPS plain text and key generating. Here you can see the plain text through the terminal using a scanf, and also the key is generated inside the HPS, and also the decrypt cipher and text written the same plain text. And after that, we are going to go to the HPS FPGA memory map AXI. Here, basically, HPS sends the 128 encryption, the encryption key and plain text to the FPGA. Communication is performed using memory mapped AXI registers. And after that, here you can see the LM used, the register IO pins and Fmax, and it is like AES-128 encryption module only. So FPGA basically receives the plain text and encryption key from HPS, and AES-128 encryption is implemented using RTL or HLS, it depends. And FPGA performs only encryption, and the encrypted ciphertext is sent back to the HPS. This is how the communication works. And here we can see the results like the integrated system, like HPS reserve receives the ciphertext generated by the HPS FPGA, and we are going to like show the demonstration on the window on the quarters, so you can better understand what we did in the project.
As we can see here, we will see the implementation of the software and hardware part for the project. So in this project here, we already generated the HPS, the .h file that contain all the memory mapping that we have, that we need for the project. So here we have generated all the mapping that required for the design for all this part, as we can see here. And then we are going to implement the AES-128 algorithm. So first of all, we are going to assert and release the enable and the key for the enable and reset for the design. And then we are going to write the keys by byte to the FPGA. And after that, we will write also the plain text to the FPGA by using this code. And also after that, we will wait for like a millisecond or more to implement the AES algorithm inside the FPGA, and then it will save the result, the ciphertext 0 address. We will display it on the software itself. And after that, the software encryption, we will validate the code, the ciphertext that we get from the Quarta software and the FPGA with the ones that we have in the system or already generated. So as we can see here, the plain text, the key is already internally generated inside the software, and the user will enter the required key, 16 ASCII key to the algorithm. And after that, as you can see here, we will implement it and return the decrypted data text. So this is for the software part. And for the hardware part, I will display the quarters. Just display this. Okay. So for the hardware part, as we can see here, I already run the program because we don't have time to run the parental. It's going to take like more than 30 minutes. So all these files are for the encryption part, as you can see here. And this one here, our top level design that connects the AXI to the design itself. So the first thing that we need to do is to see the AXI code. So sorry, the encryption algorithm. So here, this is the top design. We connected the plaintext 0 and the keys and all the ciphertext that came from the HPS part. And right now they are inside the FPGA, and it will go through all these files. These files are exactly the same that the ones that we have in the software. And after it's done, it should be go through the AXI and be displaying again inside the software. So this is the kind of co-design between the software and hardware that we have. Actually, here is the mapping for the AXI. We have used the Arial Cyclone V hardware processor, and we used the Avalon memory mapping, the second one. Actually, we were not able to use we use the AXI, not the Avalon, because the Avalon, it will require from us a license to run it. So this is the masters, and all of these, the keys and the plain text with the reset, with the memory, they will represent as the slave. So once we run this and we will finish it, we will get this window here. We will get, sorry, we will get the RTL level design. So in the RTL level design, as you can see, this big guy is the AXI, and as we can see here, these wires will bring the data from the HPS and connect it to the algorithm here. And after it does all the required computation, it will return the ciphertext again to the software, and it will display the ciphertext came from the FPGA. So right now, after we've done all of this and connect the HPS part to the FPGA part, we should be able to generate the run the SOF file here that we got on the FPGA. I will choose it, delete one of them, and after that I should have the binary file for our design. That's I already run it on the Linux system, and then I should run, after generating, I should run PuTTY here. So I'm going to do a demonstration, a live demonstration for how it can perform. So first of all, I need to enter the root. After that, I should do fdisk.l. So as we can see here, we got the files sorted and stored in this part. So I'm going to mount it. To the media folder. After that, I will go to the media folder itself. And display all the list. So as we can see here, we have the file, my AES binary file. But before I do this, I need to upload the design first to the FPGA. So it's uploading right now, the design. And after I finish, I will just run the test. So here, the system will ask the user to enter upon 16 ASCII characters. So I will enter 4 A's and 4 B's, 4 C's, and 4 D's. Once we enter, the system will generate the encryption key internally, as we can see here, and it will display the original plain text and will display the ciphertext from the FPGA, and then will give us the plain text from that went to the FPGA from the system, which exactly match the same that we have in the original one, which means we are in good shape. Okay, so to compare this and validate the ciphertext, we need to create like a golden reference for us. So in this golden reference, we are taking the software code and make it as our golden reference. So we can see here the same encryption key that we have here, and also the same plain text we are taking to the FPGA, and this is the encrypted ciphered key, and this is the decrypted should return the original plain text. As we can see here, the FPGA is not matching, the ciphertext is not matching with the encrypted data. That's because the endians of the data are not collected well inside the FPGA part, which is this part. Okay, so once it's done here, everything will be good and perfect. And thank you. As we can see here, we did our part and we implemented. So we can do another test for the design and enter another keys, characters. And it will give us also the same exact, as you can see here, we didn't input these characters, so they leave it as zeros. So you can do demonstration as much as you can. So from now, this is the project for me and my teammate, who's Ariane. And thank you so much for watching.
Yeah, thank you so much.
Have a good day. Bye-bye.